picture a forest fire. Like if you just close your eyes for a second, you probably see, those tall, dark green
Oh
pines.
yeah, completely swallowed up by massive plumes of smoke.
Right, just thick, billowing orange smoke everywhere. And your instinct, naturally, is to fear the thing you can see. I
Absolutely.
mean, you see a wall of black soot approaching, you go inside, you shut the windows, you lock it all out.
Which makes total sense from an evolutionary standpoint.
Exactly. But our mission in this deep dive is to look at a recent article from Science Advances, published in May 2026 via technoscience.net. And it reveals this huge blind spot in that natural instinct.
It really does. It kind of forces a total reevaluation of how we even assess environmental risk.
Yeah, because according to this research, the deadliest part of that apocalyptic picture, it isn't the smoke that's blocking out the sun.
Oh, not at all.
It's actually an invisible killer hiding right inside it, and, well, most of us don't even know it exists.
We are so conditioned to avoid the visible threat, right?
Yeah.
The flames, the falling ash, the choking soot. But the data we are looking at today, it isolates a secondary threat.
One that just entirely operates under our natural radar.
Precisely.
Okay, let's unpack this. Because the core of this research revolves around something called surface ozone.
Yes, surface ozone.
And it's a secondary pollutant, which means, if I'm getting this right, the fire isn't actually creating it directly.
That's right. The fire doesn't make it.
And it's 100% invisible to the naked eye. You literally cannot see it in that orange sky. Yet the data ties it to thousands of deaths every single year in the United States.
Thousands of deaths, yeah.
But, knowing it's invisible doesn't really explain how it gets there in the first place. And as someone who always just thought wildfire pollution meant inhaling burning tree particles, the mechanics of this completely threw me.
It's a super common misconception, really. When we talk about wildfire smoke inhalation, the public focus is usually on PM 2.5.
Right, the particulate matter.
Exactly. Those are fine particulate matters directly emitted by the flames. So think of it as the microscopic physical debris of the burning forest.
Like the tiny fragments of ash and soot.
Yeah, the stuff that goes straight from the fire into your lungs.
Right, the stuff you can literally physically see accumulating on your car windshield in the morning.
Exactly. But what's fascinating here is that this surface ozone is fundamentally different from PM 2.5.
Yeah, I was trying to wrap my head around this whole secondary pollutant concept, and the best way I can describe it is it's like baking a dark, toxic cake.
Ooh, I like that. Baking a cake.
Yeah, like the fire itself is basically just providing the raw ingredients. The flames burn the forest, and they release volatile organic compounds along with nitrogen oxide.
The ZOCs, right.
Right, and those are the ingredients floating up into the sky. So the fire is just mixing the batter, the sun is the oven.
That is a great analogy. But let's take it a step further because the specific type of oven really matters here.
Okay, how so?
Well, the sun acts as a massive ultraviolet oven. Those volatile organic compounds, which are essentially the natural oils, the resins, the saps inside the trees.
The stuff that makes pine trees smell like pine trees?
Exactly. That stuff is instantly vaporizing. And they mix with the nitrogen oxides, which are just, standard byproducts of anything burning.
Sure.
When they float up into the atmosphere, ultraviolet radiation from the sun literally bombards them.
Wow.
Yeah, it breaks their chemical bonds apart entirely. And it forces them to recombine into a completely new molecule, O3, or surface ozone.
And just to clarify for everyone, normal oxygen, like the stuff we breathe to stay alive, that's O2, right?
O2.
Like two oxygen atoms holding hands.
That's it. And O2 is very, very stable. But O3, ozone, has 3 oxygen atoms, and it is highly unstable.
Because of that third atom.
Exactly. That third oxygen atom desperately wants to detach and bond with something else. So when you inhale surface ozone, it travels down into your lungs and starts offloading that extra oxygen atom right onto your lung tissue.
That sounds awful.
It is. It's highly reactive. According to the source, it essentially acts like a chemical sunburn on your respiratory and cardiovascular systems. It causes severe inflammation.
That is terrifying. So imagine you are, I don't know, miles and miles away from a wildfire.
Way out of the danger zone, supposedly.
Right. You walk outside, you catch that distinct campfire scent in the breeze, but it's a beautiful, bright, sunny day. The sky looks totally clear.
Not a cloud in sight.
You might assume the air quality isn't actually that bad because you can't see the smoke. But the reality is, because the sun is shining so brightly, the sun is actively weaponizing that smoke. It's cooking those invisible emissions into a new, highly reactive gas right as you're breathing it in.
Yes. The sunlight is the required catalyst. Without the UV radiation, the recipe simply isn't finished. Those initial compounds might eventually just disperse.
So the sun is the trigger.
Exactly. With the sun, the smoke plume essentially becomes an active chemical factory moving across the sky.
But hang on, if this is happening every single time the sun hits wildfire smoke, why is it taking until May 2026 for a study like this to map out the death toll?
That's the big question.
Right, like why does PM 2.5 get all the headline attention and those purple air quality alerts on our phones, while ozone just sort of hides in the shadows?
Well, it speaks to the historical difficulty of tracking a secondary pollutant over vast distances. The article focuses really heavily on the work of Minghao Qiu.
From Stony Brook University, right?
Yes, a researcher at Stony Brook. His team finally managed to overcome this huge hurdle. You see, tracking PM 2.5 is relatively straightforward.
Because it's a physical thing.
Right, you put a sensor near the fire and you just measure the physical soot blowing past it.
Easy enough.
But tracking ozone? That requires tracking the initial invisible emissions, modeling the prevailing winds, calculating the intensity of the sunlight over several days, and then measuring the resulting chemical transformation hundreds of miles away.
Wow. You essentially have to track a ghost.
You really do. And to do that, Minghao Qiu and his team couldn't just, run a quick lab experiment over the weekend.
Right.
They had to synthesize 20 years of continuous data.
20 years. That's unbelievable.
We're talking about merging massive satellite observations from space with actual air quality measurements taken at the ground level across the entire country.
Stretched over 2 decades, which is just an incredible feat of data science.
It really is.
And the number they uncovered after crunching 20 years of that satellite and ground data, it's pretty sobering. The study revealed an average of 2,045 additional deaths per year in the United States, directly attributable to this specific fire-spawned surface ozone.
Over 2,000 lives lost annually.
Yeah.
Not to the immediate flames, not even to the visible soot, but to this invisible gas created by the sun reacting with the smoke.
And that aggregate number for the whole country is massive, but, it's easy for you to assume that risk is just spread out evenly or that it mainly affects the places where the fires are actually burning.
Which is what most people think.
Right. When we think of wildfires, we almost exclusively think of the West Coast. California, Oregon, Washington.
The usual suspects.
Exactly. But when it comes to the deaths from this sun-baked ozone, the map completely flips. The research explicitly highlights that the states accumulating the highest levels of this ozone during smoke episodes are in the southern U.S.
Surprisingly far away.
Right. Texas, Louisiana, Arkansas, Mississippi, and Florida.
This raises an important question, though, right? Because this is where atmospheric dynamics dictate the risk, rather than just proximity to the flames.
So why the South? I mean, if a fire is burning in Northern California, how are the deadly consequences showing up in Florida?
It all comes down to prevailing wind patterns and optimal baking conditions.
The oven again.
Right. When a massive wildfire burns in the west, the intense heat pushes those volatile organic compounds way high up into the upper atmosphere.
Okay.
And once they are up there, the prevailing westerly winds, like the jet stream, catch them and carry them east, right across the Rocky Mountains.
So the batter is literally moving across the continent.
Yes. And as those air masses move eastward, they eventually cool and begin to subside. They sink lower into the atmosphere as they reach the southern and southeastern states.
Oh, I see where this is going.
And what do they encounter when they sink down into Texas or Florida?
Intense, direct southern sunlight and high temperatures.
The ultimate oven.
Wow.
Exactly. The South provides the absolute perfect meteorological conditions to rapidly accelerate that chemical reaction. The UV index is high, the temperatures are sweltering, and the volatile organic compounds transported all the way from the west are suddenly bombarded with solar radiation.
So the ozone production just spikes right where dense populations live.
Yes, exactly.
If we pull back and look at the historical context here, this geographical shift reveals a really frustrating reality about our environmental progress.
It really does.
Because to really understand the gravity of this, we have to talk about the Clean Air Act. I mean, for decades, the United States has operated under this landmark legislation to reduce human-made pollution.
Right. And if we connect this to the bigger picture, to appreciate the contrast, you really have to picture what American cities looked like in the 1970s.
Before the Clean Air Act really took hold.
Exactly. Places like Los Angeles were frequently choked by this thick brown smog. People's eyes would literally burn just walking down the street.
Just from going outside.
Yeah. And that was anthropogenic, or human-caused, surface ozone. It was created because we were pumping millions of tons of unburned hydrocarbons and nitrogen oxides from car tailpipes and industrial smokestacks directly into the sunshine.
So we were providing the exact same cake batter, just from cars and factories instead of pine trees.
Exactly the same mechanism.
Yeah.
And the Clean Air Act forced a massive technological pivot. We mandated catalytic converters on cars to scrub the exhaust. We put scrubbers on factory smokestacks.
All to cut down those raw ingredients.
Right. And the article specifically notes that over the last few decades, the Clean Air Act successfully and dramatically drove down mortality related to human-caused ozone.
Which is amazing.
It is. It's one of the great public health victories of modern history.
We fixed the anthropogenic side of the equation. We cleaned up the tailpipes. But what Minghao Qi's research shows is the ultimate irony here. Nature is now stepping in to fill the exact void we just emptied out.
That's exactly what's happening.
These increasingly massive, intense wildfires are pumping out the exact same raw ingredients. And the source actually describes this new wave of fire-spawned ozone as actively nibbling away at the hard-won gains of the Clean Air Act.
Nibbling away. We managed to control the source we built, only to find that an uncontrollable natural source is escalating.
It's so frustrating.
The progress is being eroded. And it forces the scientific community to confront a very complex reality about what exactly is in this modern smoke.
Because if it took 20 years of satellite data just to track the ozone, it really makes you wonder what else is hiding in that smoke plume.
Oh, absolutely.
I mean, the article refers to modern wildfire emissions not just as wood smoke, but as a complex cocktail of substances.
A very toxic cocktail.
Right. And the ingredients they list go far beyond volatile organic compounds. They specifically mention heavy metals like lead and aromatic hydrocarbons.
Which introduces a whole new layer of toxicity. I mean, aromatic hydrocarbons are highly volatile rings of carbon that are known to be carcinogenic and deeply disruptive to cellular function.
Yeah, that's bad. But the lead is what really caught my attention.
The lead is fascinating.
How is there vaporized lead in a forest fire?
Well, it's a phenomenon known as bioaccumulation. Think about it. For the better part of the 20th century, we burned leaded gasoline.
Oh, right. Leaded gas.
I mean, millions of cars spewed vaporized lead right into the atmosphere. And that lead had to go somewhere. It settled into the soil and the forests all across the country.
Wow.
Trees absorb nutrients from the soil, and as they did, they absorbed that lead too, storing it in their bark and their wood for decades.
So the trees basically became a storage vault for our historical pollution.
Yes, a massive storage vault. And now, when these massive fires burn through forests that have been storing lead for 50 years, they unlock that vault.
Oh, man.
The intense heat vaporizes the heavy metals and sends them right back up into the atmosphere, right alongside the raw ingredients for the ozone.
So as a researcher, you aren't just looking at ozone anymore. You have an invisible cloud of sun-baked ozone, which we know causes severe inflammation in the lungs. But that same cloud also contains vaporized lead and carcinogenic hydrocarbons.
It's a terrifying mix.
So do these things multiply each other's toxicity? Like, if my lungs are already inflamed by the ozone, do I absorb the lead faster?
That synergistic effect is precisely the frontier of this science right now. Understanding how these heavy metals, the hydrocarbons, and the ozone interact, how they potentially compound their physiological impact on the human body, that is the next critical step.
They need to know how it all works together.
Right. And the source notes that Minghao Qiu and his team are actively preparing complementary studies to try and map out exactly how these substances interact.
They need to understand the full recipe of the cocktail.
Exactly.
But right as they are gearing up to do this, they are hitting a massive structural roadblock.
They are. The source outlines a significant threat to this ongoing research. According to the text, federal budget cuts are currently threatening the primary agencies that provide the data for these studies.
The exact same satellite data that literally just allowed them to uncover those 2,045 deaths.
Exactly that data. The text specifically names NASA and the NOAA.
The National Oceanic and Atmospheric Administration.
Right. These are the agencies operating the satellites and maintaining the ground-level sensor networks that make a massive 20-year data analysis even possible.
Yeah.
And the article reports that both NASA and the NOAA are facing proposed reductions that would cut more than a third of their science budgets.
And just to be absolutely clear here for you listening, we are just reporting the facts exactly as they're laid out in the Science Advances article and the surrounding coverage.
Yes, strictly reporting the text.
We aren't taking any political stance on federal spending. But the practical reality of the situation, as the source describes it, is that a one-third reduction in the science budget directly impacts the tools required to track this phenomenon.
It's a huge impact. The complexity of tracking secondary pollutants over a multi-day journey from California all the way to Florida. It requires sustained, high-level data collection.
It's just incredibly data intensive.
Very.
Yeah.
And if those budgets are reduced as proposed, the text suggests that the scientific community's ability to monitor these complex chemical reactions, predict where the ozone will pool, and ultimately protect public health could be fundamentally compromised.
So what does this all mean? Let's just look at the whole board here. We started by looking at a picture of visible smoke, right?
Right.
That towering, majestic, terrifying orange plume over a burning forest. But we discovered that to understand the real danger, we had to look at what we couldn't see.
The invisible threat.
We found surface ozone, an invisible gas baked into existence by ultraviolet sunlight interacting with vaporized tree sap. We learned about the staggering toll of 2,045 annual deaths.
Every single year.
Yeah, and we explored the atmospheric mechanics that cause this invisible burden to fall heaviest on southern states far, far from the actual flames.
Texas, Florida, all of them.
We saw how this natural phenomenon is eroding the historic victories of the Clean Air Act. And finally, we realized that our future understanding of this toxic heavy metal smoke cocktail, well, it relies on satellite data that is currently facing the threat of significant budget cuts.
It illustrates perfectly that the environment operates as a highly complex, interconnected system.
It really does.
A local fire is never just a local event. It becomes a secondary health crisis halfway across the continent, driven entirely by atmospheric chemistry and sunlight.
Which is wild.
It is.
That is.
Which leaves us with a critical, lingering question for you to consider. We have established that sunlight is the crucial catalyst, the oven, that transforms these wildfire emissions into deadly ozone.
All right, the oven.
But our climate is not static. So how will changing global weather patterns alter this recipe in the years to come?
Oh, wow.
Think about it. If we begin to see macro shifts in cloud cover patterns, or if regions like the South experience even more prolonged, intense heat waves that bathe these smoke plumes in harsher solar radiation, how will that alter the toxicity and the geographic reach of this invisible killer?
I mean, if the oven gets hotter, the recipe might just get even deadlier.
Exactly.
It is a lot to think about, and it completely changes the way you look at a sunny day when you can just catch that smell of smoke in the air.
Thank you for joining us on this deep dive. We really hope this conversation gives you a new lens through which to view these complex environmental issues and encourages you to just keep looking beyond the visible. Until next time.